Okay, so this is 13.6 continued. So let's look at an example. It says use the gradient to find the directional derivative of the function at point P in the direction of PQ vector. So here's our function. It's 3x squared minus y squared plus 4. Our point is -1, 4, and our q should be equal to is 3, 6. So this is our x0, y0, and this is our x1, y1. So if you think about where we're looking at this, we have our point P here, and our point Q here, looking at the derivative coming along this direction. Okay, so note, let's find our gradient. So our gradient, again, by definition, is defined to be the partial derivative with respect to x, I direction, partial derivative with respect to y, j direction, and partial derivative with respect to x. Well, here's a function here, so partial derivative with respect to x, we're treating the y as a constant. It's going to be 6x. And the partial derivative with respect to y, so like in this guy over here, partial derivative with respect to y, treating the x as a constant, it's going to be -2y. So hence, our gradient in our case will be 6x I minus 2y j. Also, let's look at the vector PQ. This is going to be the difference of point Q and point P. So our Q guy is 3, 6. Our P is -4. So simplifying this, it would be 3 minus, it would be 4. Okay, write the vector notation here. Be 4, and 6 minus 4, 2. Okay, so now let's find the magnitude of PQ. So magnitude of PQ is the square root of first component squared, so 4 squared, plus 2 squared. So that check the square root of 20. So hence, I move this over here. So hence, to find our u now is the unit vector, so we need to normalize our PQ guy. So to normalize, you just take our vector and divide by magnitude. Okay, so our magnitude is square root of 20, so it's going to be 1 over square root of 20 times our vector. Let's write it this way. Let's write it as 4i plus 2j. Okay, so that's our u. So it follows, we're going to use now theorem 11. By theorem 11, when we proved in the last video, we know the directional derivative at a point which is -1, 4. It's going to be the gradient at -1, 4 dotted with our u. Okay. Note. So again, I guess I can't see the gradient up there, but let me write again. The gradient, we already found the gradient in general, was 6x I minus 2yj implies, so when I evaluate the gradient at negative 1, 4, so the gradient of negative 1, 4 will be 6 times, so negative 1 in place of x, 4 in place of y. So it will be 6 times minus 1 I plus, minus 2 times 4j, so it will be negative 6i minus 8j. Okay? So now, plugging into this then right here, so we found our gradient of negative 1, 4, so it's going to be negative 6i minus 8j dotted with our u is this guy here, be 1 over square root of 20 times 4i plus 2j. Okay, so the 1 over square root of 20, you can just bring in front of the dot product here. So it'll be 1 over square root of 20. That'll be negative 6 times 4, so it'll be negative 6 times 4 plus this times that, so it'll be negative 8 times 2. So it would be then negative 24 and negative 16, so negative 40. So negative 40 over square root of 20. So that's our directional derivative at our point negative 1, 4. Okay, so let me pause it here for a second. Okay, let's next continue with theorem 12, which is properties of the gradient. So we're going to prove these two properties. So property 1, it says if the gradient is 0, then the directional derivative is 0 for all directions coming into x0, y0. And property 2 says the direction of max increase of f is given by gradient. Moreover, max value of the directional derivative is the magnitude of the gradient. So let me just explain 2 a bit here so you can understand what it's saying. So imagine here's my xy plane, and you have a point x0, y0. You can come into the point from many different directions in the xy plane. And above our xy plane, we have some surface. I'll make it simple enough here, my surface, just something like that, say. So coming into a point x0, y0, which direction would we increase on the surface the quickest? So you can see here, say here's the xy plane here. If I come in that direction there, I'd be going up on the surface the quickest. So that'd be a max increase. So therefore, my gradient should be pointing in that direction in the xy plane. So it'll go like this, I guess. You can see then the gradient would be pointing in a direction where you'd increase on your surface the quickest. Okay, so that's what property 2 is saying. So let's prove this theorem. So prove. Let's do property 1 first. So suppose, if, say, the gradient at x0, y0 was equal to 0, what do you mean by that is 0i plus 0j, then by theorem 11, we have that the directional derivative of x0, y0 will be, this, dotted with cosine I sine j. Okay, well, we're assuming that this guy is a zero vector. This would be then 0i plus 0j dotted with cosine. Again, this is our u. Cosine I plus sine j. But when you dot those, you get 0 because you got 0 times I, 0 times the sine. So pretty much you dot those, you get 0. So this proves 1. Proves property 1. Okay, now let's prove property 2. So to prove property 2, proof of property 2, so recall actually you put it up here. So do my recall here. Recall we proved the Friedrich theorem was a while ago. Given two vectors u and v, we know that u dot v equals magnitude of u, magnitude of v, cosine of theta, where theta is the angle between the vectors. Let's recall that as a sidebar. It follows by theorem 11 again, by theorem 11. So write out our theorem 11 again. So the directional derivative at x0, y0 equals gradient x0, y0 dotted with u. So applying this guy to this one here. So this would be then, I guess the u would be the u, this would be the v. So you can think of this as the v. This would be then magnitude of the gradient times magnitude of u. But our u, by definition, is a unit vector, so this is equal to 1. Because since u is equal to cosine I plus sine j, so if you do the magnitude of u, the square root of cosine squared plus sine squared, that guy is 1 in there, so this whole thing's 1. So this just equals then the magnitude of the gradient times the, sorry, I forgot the cosine of the angle, sorry. Cosine of theta here. So we still have cosine of theta here. So we have a directional derivative equals the magnitude of gradient times the cosine of the angle. Here we have our gradient guy here, and our u guy here. It's an angle. So therefore, what direction would we have to choose u to maximize this? Well, you have to choose u in the direction of the gradient, so pretty much the angle has to be 0 to maximize. So note, max occurs when cosine theta equals 1. And min occurs when cosine theta equals -1. So hence, max at theta equals 0 and min at theta equals 180. Okay, so we've proven then P2. So proven that the max value would have to be then the magnitude of the gradient. So we're done with this.